of quadratic functions. Here in this section, we're going to be looking at applications of all we've been doing with quadratics. So let's just kind of review some things that we know. When we're looking for a minimum or maximum on a graph, this is when we are looking at the vertex. And remember, we talked about how when we have a parabola, this would be our minimum value. And then when it's facing downward, this is going to give us a maximum value. So when you're looking at these application problems, when do we know we want to look at the vertex? Just know that you're looking for when it's minimum or maximum. And it may be asking for the h or the k of that vertex. We'll have to look at how it's worded in the question. If in the application problem it's starting about the initial or starting value, it's going to be representing or trying to show you what the y-intercept is. If we're looking for a stop, this is going to be when we're looking for the x-intercept. We have to look at the possible one. We know how to solve for x-intercepts, but we need to make sure we're using one that's applicable to the problem. And a lot of times in these situations, we're going to be looking at the quadratic formula because numbers are not always nice out in the wild like this. Like it's not always just 2s and 3s. So let's just kind of reference that and look to that as we work a couple of examples. It says this ball is thrown upward from the top of a 40-foot building at a speed of 80 feet per second. The ball's height above the ground can be modeled by the equation. So everything they just said in those first two lines, it's telling you how they set up that equation. It's important to note that it says the ball's height. So that means this is height. And then t is going to be representative of your time. So this is going to be time. It's important to note what units these are. So this is time in seconds. So I'm getting this from this over here. And this is going to be our height in feet. So it asks a couple of questions. When does the ball reach the maximum height? So we're looking for when and max height. Well, if you consider this quadratic, it looks something like this. It is a quadratic that is facing downward. I know this because of this negative on this 16. I know it's a quadratic or it's a parabola because it's a t squared. So if I'm looking for when does the ball reach max height, right here is max height at the vertex. And so for part A, I want to find that vertex. I'm going to use h equals negative b over 2a. Let's see, b would be 80 over 2 times negative 16, just like we've been pulling those a and b values. Cleaning that up, that gives me negative 80 over negative 32. Or using your on-screen calculator, that reduces to 5 over 2. So when does the ball reach the max height? After 2.5 seconds. We always want to make sure that we apply to the given situation. So a lot of times you use that 5 over 2, but in this case, someone's saying, when does the ball reach max height? They're like 5 over 2. I don't know what you're talking about. Or you have to interpret that for them. 2.5 seconds. Now, step 2 says, what is the max height of the ball? We know when it occurs, that's at 2.5 seconds. What is the height of that ball? That's going to be that y value when we go and plug it in. So in order to do part B, we're looking at our k value of our vertex. So that means just plug in your 2.5 into your given function. So it would be negative 16, 2.5 squared plus 80 times 2.5 plus 40. Use your on-screen calculator, and that gives me 140. And again, we already mentioned that's our height in feet. And so that is your vertex graphically, but application-wise, that is when it hits at max height and what the max height is. Next part says, when does the ball hit the ground? So when does it hit the ground or stop? We're looking at these x-intercepts. Now in this application, right here is 40 feet, and this is when the ball is being thrown off. So we're not concerned about this side of the parabola. So we're only going to be looking at our positive answer with our x-intercept. So for part C, we're going to be looking at the x-intercept. By all means, we're going to be using our quadratic formula. And although mathematically it gives us two answers, we're just going to use the positive answer. And so as always with your quadratic formula, identify your A, B's, and C's. A is negative 16, B is 80, C is 40. So X is equal to, or as we were talking about, this is representing our time or a T. So I'm going to say negative 80 plus or minus the square root of 80 squared minus 4AC all over 2A. I'm going to use my on-screen calculator to help me with that, so I am going to plug this in to the calculator, and it's going to give you two answers. I'm going to get negative 0.458 and positive 5.458, just rounding the 3 decimals. These are seconds, but we don't want negative time. So when does the ball hit the ground? At 5.458 seconds. You can see in this application of this problem, it's all the things we've been doing with quadratics, vertex, x-intercepts, but we have to apply it, and the picture can be really helpful for where am I looking, what am I looking for. I would like to do another example and kind of see how these quadratics are going to play into this. It says Marcus wants to build a rectangular enclosure for his animals. One side of the pen will be against the barn, so he needs no fence on that side. The other 3 sides will be enclosed with wire fencing. If Marcus has 750 feet of fencing, find the dimensions that maximize the area of the enclosure. So a picture is just so helpful when working a situation like this to put everything in the right places. So he's building a rectangular enclosure. And so here's my rectangular enclosure. And it said that one side of the pen will be against the barn. And so here is my barn, and then there's my enclosure. So the other 3 sides are enclosed with wire fencing. If Marcus has 750 feet, so this is perimeter because he's putting a fence around it, find the dimensions that will maximize the area of the enclosure. So we're wanting to maximize this. Part A says let W be the width of the enclosure. Okay, so if W is the width of the enclosure and L be the length of the enclosure, write a function for the area of the enclosure. Okay, so part A. I'm going to first write a situation to represent this area. Well, I know that area is equal to length times width. And I don't really have much more information, but this is where the perimeter comes into play. Perimeter is going to help you to create your area equation into one variable, because right now I've got L's and W's. So going back to that 750 feet perimeter, we're going to say, okay, well, twice the width plus the length should be a total of 750, because I am just adding up these 3 sides in order to build my fence. Then I'm going to use that information in order to plug into the area equation to just get one variable. L looks like a good variable to solve for itself because it's already by itself right here. So I'm just going to subtract 2W from both sides, and that gives me my length is equal to 750 minus 2W. So I'm going to take that information and I'm going to sub it in over here to area. So area would be equal to, instead of L, I'm going to say 750 minus 2W times W. And you may have been wondering, why are we even doing this? We've been working with quadratics. Well, when I distribute that into this, that gives me 750W minus 2W squared. And I now have a quadratic. If you'd like, I can put this into that standard form of ax squared plus bx plus c. So it would be negative 2W squared. Positive 750W plus 0 if you're looking for that C value. So in B it says, what width would maximize the area? So what I'm going to do is I'm going to find the vertex of this parabola. This is a downward facing parabola. It looks something like this. It represents my area. So max would occur here at the vertex. So I would say, okay, that would be equal to negative B over 2A. So we do negative 750 over 2 times negative 2 gives me negative 750 750, getting ahead of myself, over -4, which reduces to 187.5 feet. This is representing our W in this case. So what width would maximize the area? The word maximize, you want to think vertex, and W is representative because that's, instead of our X, we have that W. So that means that would be the width that would maximize it. Now, what is the maximum area is when you plug it back in. So let's see, this was part B. And so this would be part C. We would say, let's take our area equation, and then we're going to plug our number that we just got back in. So it would be -2 times 187.5 squared plus 750 times 187.5. And using your on-screen calculator gives you 70,312.5 feet squared because we're looking at area. So this one definitely was a little bit more confusing because you didn't really have that quadratic at first glance, but you had to piece all that information together. And that's why we've been building up to this point, working with the basics of quadratics and now applying it. I'm going to do one more situation, and then we'll move on to the homework and see what you need help with there. It says the demand equation for a certain product is given by P equals 138 minus 0.05x, where P is the unit price of the product and X is the number of units. The total revenue obtained by producing and selling X units is given by R equals XP. Determine the price that would yield a revenue of $7,570. So let's just kind of recap that. May have lost you already. They said that the price was your P function. P equals 138 minus 0.05x. Then they said revenue is X times P. So we're going to say X times, and we're going to plug in what P is equal to, 138 keep doing that, minus 0.05x. So if I distribute this X, I get 138x minus 0.05x squared. And so there's my quadratic. That's how this is fitting in here. Well, we want to know, determine the price P. So we're trying to find the price P that would yield a revenue of $7,570. So that means I'm going to set my revenue equal to that number. Now that I have a quadratic situation, I always want to get it equal to 0 so we can solve. So I have 0 equal to, and I'm just going to rearrange these in order of descending exponents, keeping all my signs what they should be. Quadratic equal to 0, and especially with these type of numbers, I would just jump into my quadratic formula. So I'll say negative b plus or minus the square root of b squared minus 4ac. And like we've done before, if you need to take those steps and identify your A, B, and C, write your formula, do all those processes. But we've been doing it on repeat, so I'm just filling it in. When you plug this into your calculator, this gives you two values, 2704.009 units, as well as 55.991 units, because it's always going to give us those two answers. Now, make sure you go back and answer the question. Okay, we got X equals. What does that even mean? And that's how many units. Up here, it said to determine the prices that would yield a revenue of that. So I'm going to go back to my price equation, which was 138 minus 0.05x. And I'm going to plug in these two values. When I plug in the 2,704, I get a price of $2.80. And when I plug in the 55, I get a price of $135.20. And so these are the two prices that would yield this revenue. Again, lots of application here. Hopefully you've already got those base skills, being able to solve a quadratic, and then we're just taking it up a step. But as always, go and attempt the homework and then reach out to your instructor if you need any assistance.